All right, folks, this is video number 3, section 5-4, and we're still in the discrete probability distributions. There's this one here we're going to talk about is called, the way you say it is Poisson, P-O-I-S-S-O-N, Poisson distribution. There's 2 times that you're going to use it. You're going to use it kind of like a binomial distribution. It's a way of approximating the binomial distribution. So that's method number 1, or use number 1. Use number 2 is when the independent variables occur over a period of time. Now, it doesn't have to be time. It could be a period of length or density, a variety of things. But oftentimes we do it with time, and we'll see an example or 2 coming up here. Okay. All right, so I'll go ahead and let you read this. So it doesn't have to be time. It could be the number of plants growing per acre, or the number of defects in a given length of videotape. So that's not time, but everything is a metaphor. You can use it for time, you can use it for acre, you can use it for a given length of videotape. All right, so that's a very common distribution, or a very common use of the Poisson distribution. And then it's used less often, I would say, to approximate the binomial distribution. And the reason why it's used less time is because we really don't need these approximations that much anymore, because we've got the computers that can calculate these things very, very quickly. All right, so anyway, here's the definition. Probability distribution. Here are the certain requirements. X is the number of successes, as always. We're always talking about number of successes. And it's got to be over some interval. Okay, the occurrences occur randomly. The occurrences are independent of one another. So there is, if your sampling is with replacement, and the average number of occurrences over some interval is known. So essentially what we're doing here is, if we know the average, we know the mean number of occurrences over a period of time, then we can estimate, we can calculate the probability of getting a certain number of successes. So we'll see here in just a little bit, but one of the examples I like is if you're the city manager and you know that there's going to be a certain number of fires per day, you can calculate the probability of there being 3 fires, the probability of being 2 fires, and so forth. So it's kind of that sort of problem is used. We use the Poisson distribution. So here's the formula. The probability of X occurrences. So X is the number of successes, and at some interval of time, okay, or it could be a volume, it could be an area, for some variable where lambda, this is how you say it, call it lambda, is the mean number of occurrences. So it's the expected value, the mean number of occurrences per unit time or volume or what have you. Okay, so if you know how many fires per day, that's your lambda. If you know how many defects you have per meter of wire, that's your lambda. And here's the formula. It's kind of a messy formula here. I'll let you read that. Okay. E is Euler's constant, but it's just a number. For our purposes, we just use it as a number. It's used in the exponential function as well. You may have seen that in Math 35. Okay, so let's talk about it right here. The typographical errors. Okay, now, as always, these are metaphors, just that they're examples that are easy for us to understand, right? I find that people tend to think that, this stuff is so boring because we don't care about these examples, but these examples are just to illustrate the problem. When you get into your other classes, you'll find examples that are a lot more interesting. Okay, so now let's talk about this problem. We have a 500-page manuscript. Okay, and we want to find the probability that on one specific page, a given page, it has exactly 3 errors on that page. Okay, so the first thing we need is the mean number lambda of errors, because there it is, there's the formula. So we need to know what lambda is. We have to calculate that. Okay, so the lambda is the mean number of errors. Errors is the random variable that we're looking at. There's 200 errors throughout the entire book of 500 pages. Therefore, each page has an average, an expected value of 200 over 500, which is 2 over 5, which is 0.4. So there's 0.4 errors per page. And just like we've talked about before, obviously you can't have 0.4 errors. You have to have it's an error or it's not an error. However, this is an expectation, so it's okay to have something for the mu. It's okay to have the expected value be something that it cannot be a real value. That's perfectly okay. That's a theoretical value. Okay, so there's 0.4 errors per page. X is equal to 3. So we go up here to our formula. Okay, E is just a number to the power of minus lambda. So I hope you remember what that means. E to the negative lambda means it's the negative exponent means it's 1 over e to the lambda. Okay, which he does not really write out here, unfortunately, but that's what it means. And then you've got lambda, which is the number we just calculated, the 0.4, raised to the power of x, which is 3. X is a counting number. It's 0, 1, 2, 3, and so forth. And then on the bottom, we have x factorial. So we're not going to, it's beyond the scope of this class to prove that this formula is correct. We're just going to use this formula. Okay, so you plug in all the numbers, and there you go. There's the probability. That's what we need. So there is less than 1% chance that at any given page will contain exactly 3 errors. Okay, so this gets to be complicated, to say the least, right? Now, not so much anymore because we used to have calculators to do all this, but back in the day, it's too hard. So what we would do would be create these tables. So we have these tables. I'm going to let you look at that. It's table C in the appendix in your book. Okay, and it gives the probability, gives P probability for various values for lambda and for x. Now, I hope this notation was reasonably clear to you. It's P, that's probability, and then in the parentheses here, we have X, that's the number of successes, and then a semicolon here, and then lambda, that's the mean number of occurrences, the mean number of successes per unit time. So the notation is a little tiny bit different from what we've been saying. Okay, so in any event, if example 5-28, that's the example we just did, okay, lambda is 0.4, so that's up here. X is along this column here. There's 3 successes with a lambda of 0.4. It gives you the calculation. Some guy sat down and did the calculation and put it into this table, and that's exactly the same answer as we got by doing it by hand. Okay, so we got toll-free phone calls, the same basic idea. I think what this is trying to teach you is how to understand this language. When we say at most 3 calls, at least 3 calls, what does that mean? Okay, so at most 3 calls means 0, 1, 2, or 3 calls. At least 3 calls means 3 or more. Okay, so that would be 3 calls. Hold on one second here. Oh, okay, what he's saying here is the following. Okay, so the problem starts out by saying that they get on average, that's the mean, that's your lambda, you get 3 calls per hour. So for any given hour, what's the probability that it will receive? And then here's the 3 parts of the question, A, B, and C. So at least 3 calls means it will get 3 calls at least. So it could get 3, it could get 4, it could get 5, it could get 6. It could just keep on going. Now it's going to become vanishingly small. The probability of getting 100 calls is going to be so close to 0 that you don't even care about it, right? But it's just too tedious for us to calculate it that way. For us to calculate 3 calls, 4 calls, 5 calls, that's just a pain in the neck. So why don't we do it this way? Why don't we say, well, at most 3 calls means you get 0, 1, 2, or 3. So if we wanted to find out what's the chances of getting 3 or more, it's easier to find the probability of getting 0, 1, and 2 calls and then subtract this answer from 1 to get the probability of at least 3 calls. It's finding the complement. We've done this before where if it's too hard to calculate the one thing, we calculate the complement and we subtract that from 1. So that's exactly what's going on here. At least 3 means 3 or more. So we calculate the probability of 0, the probability of 1, and the probability of 2. That gives us these numbers from the table. That gives us a final answer of this. And then 1 subtract that number is this number, and that's the answer we're looking for. That's the probability of 3 or more. 5 or more, same exact concept. 5 or more calls. It's a lot easier to calculate the probability of getting, excuse me, I had to pause. It's a lot easier to calculate the probability of getting 0 calls. That's right here. The probability of getting 1 call, that's right here. Probability of getting 2 calls, and so forth. And then you subtract that answer from 1. So that's what he's doing there, okay? Okay, so at the very beginning, the author said, well, there's 2 ways that we use the Poisson distribution. We use it if we have the average number of occurrences, the average number of successes, and we use that to calculate a particular number, a number of successes. So that's one way of doing it. And then the other way we can use it is right here. It's used to approximate the binomial distribution when this expected value, the expected value is n times p. Okay, so now, unfortunately, there's a typo here. The expected value y equals n, and then that looks like a decimal place, n p. All right, what it should say, and it is correct in the printed version of the book, at least in my edition it is, it should be lambda equals n times p is less than 5. Okay, so it's lambda equals n times p. See, now the reason for this is that if you remember from the binomial distribution chapter, the expected value in a binomial distribution, the expected value, the mu, is n times p. If you toss a dice 100 times, what do you expect? How many heads do you expect to get? N is 100, p is a half, so 100 times a half is 50. You expect to get, on average, you expect to get 50 heads. Okay. Well, we can use the Poisson distribution to approximate it. Now, why would we do that? Probably not so much anymore. It's just an interesting mathematical concept. So let's see if we can do this. Approximately 2% of the people in a room of 200 people are left-handed. Find the probability that exactly 5 people there are left-handed. Now we could do this. We could figure this out using the binomial distribution. In fact, he does it right down here. If you remember the formula, the binomial distribution, we have this, n choose 5, and it's a combination. So n choose 5. There's 5 people. There's 200. N is 200. So it's n choose 5. So it's 200 choose 5. That's the C. You have to figure that out. There's a formula for it. And then this right here, that's the probability of success. The probability of success is 0.02. And there's 5 of them. So 2%, 5 of them is 0.02 raised to the 5th power. We multiply 0.02 times 0.02 times 0.02. We do that 5 times. And then the probability of failure, the probability of being not left-handed, is 0.98. And that's going to be the rest of the people. 5 people are left-handed. That means 195 people are not left-handed. So it's 0.98 raised to the power of 195. So if you crank this out on your calculator, you come up with this number. So you could do this. You could do this using our original formula for the binomial distribution. However, right now we're trying to do it by way of an approximation. So you plug it in. Lambda is equal to n times p. See, that's he made the mistake up here, but he didn't make it here. Lambda is n times p. Okay, crank that out. Crank it into the formula, and you come up with this answer, and that's about the same as this answer. The difference between the answers is based on the fact that the Poisson distribution is an approximation, and we've used rounding. So those numbers in the back of the book and that table, they're not exact. They're rounded off, I guess is what I'm trying to say. Okay. All right. So that takes care of this. That's the end of this video. Next, we're going to talk about the hypergeometric distribution.